First of all, thank you for all of us. We are here face to face, for our participants online, and thank you, Professor KOIKE. And now let me start on time by opening remarks by President Al-Balqa University, Professor Dr. Ahmed Fakhri.
Your Excellency, Mr. Shumaski, Ambassador of Japan, Your Excellency, Dr. Hazem Al-Nasser, esteemed guest lecturer, Professor KOIKE, Toshio, Director, International Center for Water Hazard and Risk Management under the species of UNESCO, and dear member of audience who are watching us online through different social media in Jordan and Japan. Firstly, I would like to begin by expressing my sincere gratitude to Mr. Shumaski for his kindness in personally attending this lecture at Al-Balqa Applied University, as well as arranging to have our distinguished lecturer, Professor Dr. KOIKE, for his seminar on climate change and its impact on water problem in Jordan. Your Excellency, thank you for choosing this topic, which is very important to us in Jordan. It's our great honor at BAU to share with our audience a valuable theme that can be summarized in two words: climate and water. Equally important is discussing its huge impact in the whole world, especially in the light of recent natural disaster that has been increasing in incidence. The interplay between climate change and water are crucial to our response to climate change, which are undeniable phenomena hitting our world. Its aftermath extends beyond our expectation and will live for generations to come if we do not act soon. No one can imagine what is going to happen in the next decades if we refuse to act urgently and efficiently. Climate change and its widespread impacts, which are the theme of today's lecture, will keep in deteriorating and impacting our life and environment if we do not collaborate to urgently address this issue. Consequently, I invite everybody joining us today in formulating a strong and urgent call for collaboration and cooperation between our nations to hopefully be able to help the next generation avoid the projected destructive consequence of climate change. Dr. KOIKE in today's seminar will demonstrate a great example of how we, the academic institution, will collaborate to share our experiences and explore further collaboration among us, and especially in Jordan, where water is a precious resource. Jordan, as you all know and aware of, is considered one of the top 5 countries in the world in terms of water scarcity. In fact, during the last year, water resources in Jordan have marked the lowest point ever throughout modern history, where water demand has crossed its red line due to drawback of rainfall. In very simple words, there was no rain last year, a clear and undeniable consequence of reality of climate change. I join my audience in expressing excitement of hearing from Professor KOIKE and seeing what kind of experience Japan and others have in the context of climate change. Additionally, the talk will better inform us how they work in adapting and preparing for climate change impact, what kind of measures have been taken at local, regional, and international level in facing the impact and hazard of climate change. Finally, and particularly relevant to our geographic context, we will better understand the water crisis prospect in our regional and how it will look to be in the future. Without any further delay, please allow me to give the floor for our esteemed guest. Let me thank you all for your attendance and thanks to the Embassy of Japan for facilitating such fruitful joint lecture between Jordan and Japan. Thank you all. Thank you, Professor KOIKE, for your time and contribution.
Minister of Water and Irrigation, Professor Dr. Ahmed Al-Ajuruni, President of Al-Balqa Private University, Doctor of Engineer Koike Toshio, Director of International Center for Water Hazard and Risk Management, distinguished guests and dear listeners. It is our great pleasure to hold this online seminar on climate change and its implication on water issues in cooperation with Al-Balqa Private University. I'd like to express my sincere appreciation to President Al-Ajuruni and Dr. Mohamed Madok for their efforts to realize this opportunity. I'm excited to hold the seminar on the crucial issues of the world, as well as Jordan, climate change and water, in the leading university in the field. Climate change is one of the biggest challenges we all are facing today. Of course, Japan is no exception. In November last year, Prime Minister Kishida attended the COP26 World Leaders Summit at Glasgow, during which he stated his own determination that Japan will be working in full force to take on climate change, a common challenge of humankind. Japan also understands the importance and gravity of the water crisis in Jordan and places it among its priorities of our ODA policy for Jordan. Last year saw the signing of a grant agreement worth $23 million as part of our ongoing support for the Zai water supply system. We will continue focusing on water issues in supporting Jordan. Today, we are going to listen to a presentation on the nexus of the two important issues by one of the leading Japanese scholars, so namely Dr. Koike in the field, followed by a response speech by one of the most prominent Jordanian figures in the field. I hope this seminar attracts attention of many Jordanian students and scholars and makes them consider future efforts. Moreover, it would be worth mentioning here that every year the Embassy of Japan selects 4 to 5 Jordanians as governmental scholarship students. The selected students will be given full scholarship to get degrees in Japanese universities with excellent professors and curricula. The application for the next batch will open from next spring. So if you get interested in the advanced researches in Japan, as being represented today by the works of Dr. Koike, I would like to recommend you to check it out to realize your potential in Japan. Finally, let me reaffirm our enthusiasm to strengthen cooperation with Jordan in many fields, especially in science, academia, and culture. We will continue making opportunities for Jordanians to know Japan in its diverse aspects and strengthening people-to-people ties between our two countries. Thank you very much for your kind attention.
Thank you, Your Excellency, for very beautiful and very impressive works. And now, let me introduce to you our guest speaker and start our live lecture today. We have today Dr. Koike. Dr. Koike, now you are the host. When you start your speech, you can start when I finish an introduction. Thank you very much for your attendance again, and it's our pleasure to see you here as in virtual and face-to-face. I will not speak a lot. I just want to introduce our guest speaker, Professor Toshio KOIKE. He is an Executive Director of the International Center for Water Hazard and Risk Management under the auspices of UNESCO and Professor Emeritus of the University of Tokyo in his capacity as Chair of River Council of Japan since 2015 and a council member of the Science Council of Japan Cabinet Office since 2017. He has also helped and improved the development various aspects of infrastructure design and science native work via provision of policy recommendation to the government and the public. Some of the prominent awards he has won recently include award for contribution to the EPCC Nobel Peace Prize from WMO and UNEP. In 2008, Einstein Lecture Award in 2009 and from Chinese Academy of Science and Individual Excellence Award from the Group of Air Observation EOO in 2020. We now all welcome our guest speaker, distinguished guest speaker. The floor is for you, Dr. KOIKE, and please start.
Thank you, Professor Dr. Mohammed Matuk. His Excellency Dr. Hazem Al-Nasser, former Minister of Irrigation, Professor Ahmad Al-Ajrohi, the President of Al-Balqa Applied University, and Ambassador Kaoru Shimazaki, the Japan Embassy in Jordan, and a distinguished guest, ladies and gentlemen. It is my great pleasure to have this opportunity with regard to the climate change and its impact on water problem, especially in your region. So I would try to discuss two topics, two questions. One is, as the climate system changes, does agricultural and ecological drought increase? This is the first question. Second question is, as one of the climate change adaptation measures, can we monitor and predict agricultural drought? So we would discuss these two questions in my talk. Firstly, to consider the first question, we would discuss about fertile climate system. All energy of the phenomena of the Earth come from the sun. And sun energy absorbed by Earth system and heat up our Earth. According to the temperature of the Earth, a long wave infrared emission occurs. So, but actually more the atmosphere surface distribution. I would focus on the three components in this sphere. So almost half of the energy by Earth is emitted. Three types of the process. One is the radiation. Yes. And the other one is the sensible heat transfer. So our surface is become warmer, and then a wind blows, and that heat is passed to the atmosphere. So then we have a warm Earth. And you experience very well. So by sprinkling the water on the surface temperature become cool. Then the liquid water is evaporated, and latent heat is absorbed. So in this way, we have warm air mass and wet air mass. I have two questions to you, but this is not a face-to-face discussion. That might be a little bit difficult to manage. Cool air mass and warm air mass, which is heavier? Maybe you know well. cool air mass is heavier. Yes. So next question. Wet air mass and dry air mass, which is heavier? In a class case, I asked the student to raise hand, but the more than 95% student make a mistake. They think wet air mass is heavier, dry air mass is lighter, but actually opposite. So regardless of the kind of the gases, same number of molecule is included in a certain volume of gas and a certain temperature and pressure. Same number, regardless of the kind of the gases. So that's why dry air mass consists of the nitrogen and oxygen. The weight is 28.8. But water, the H2O, the weight is 18. Same number in a certain volume. So this is the perfectly dry air mass. Only oxygen and nitrogen. This is a little bit wet air mass. This is very wet air mass. So the same number of molecules should be included in the certain volume and a certain temperature and pressure. So dry air mass heavier, wet air mass is lighter. So that's why warm air mass is lighter and go up, lifted up, and warm the atmosphere. Then wet air mass is also lighter and go up, and upper temperature is cooler. Then water vapor is saturated and condenses into the water droplet, that is a cloud. So at that time, this latent heat is released and warm up the atmosphere. So more than half of the energy is transported by water vapor to the atmosphere. And after the meeting of the small cloud droplet and become a large water droplet, that is a rain drop. And due to the gravity, it goes down. So due to this vertical transport of the water, so the more than half of the absorbed energy by the Earth is used for heating up the atmosphere in this cloud. First thing, satellite image. So ocean is darker and land is brighter. Brighter means reflection is larger on the land. Darker means absorption is larger. So that's why ocean is absorbed more energy. And ocean is water. So enough water. So that's why by just atmosphere over land, because the water is limited on the land and smaller energy is absorbed. But such quite different temperature gradient, such a large temperature gradient cannot be observed. Why? Over ocean, rainfall is larger than rainfall is smaller than the evaporation. And on the other hand, on the land, rainfall is smaller than rainfall is larger than the evaporation. So ocean, evaporation is larger, rainfall is smaller. That's why ocean surface go down. And on the other hand, over land, rainfall is larger than the evaporation. That's why it should be inundated. But due to the gravity, the water is go down according to the slope. and enter into the ocean and compensate this gap. This is the land process, earth process phenomenon. In the atmosphere, the rainfall is smaller and evaporation is larger. So atmosphere over become wet and wet and wet. But due to the transport of the atmosphere, this wet air mass is transported over land, and only the vertical process. This should be cooler, so that light condense and then cloud formation and rainfall happen. So in this way, the water cycle plays a key role to form our climate system. That's why climate change, the water cycle should be changed. You can understand. Our Earth is a sphere, so that's why a high latitude area absorbs the smaller sun energy, and the low latitude area absorbs the larger sun energy. So this the very large discrepancy of the absorbed sun energy in a lower latitude and a higher latitude, you can understand. This red line is the distribution of the longitudinal distribution of the infrared radiation, outgoing radiation. Of course, the higher latitude, Earth's surface temperature is lower. That's why this long wave radiation is smaller than the long wave radiation around the equator, of course. But the gradient is quite different. So that's why in a lower latitude, the energy is surplus, and a higher latitude deficit. To compensate this gap, atmospheric circulation and ocean circulation is generated. And this suppressed energy is transported to the higher latitude by the ocean circulation, ocean current, and also the atmospheric circulation. This is the general circulation of the Earth. According to that process, your country is very critical. So this atmospheric circulation from the equator to the pole side divided into three parts. This larger part is called the hardware circulation, and along the equator it's upward wind, and then around your region it's a subsidence. So that's why every day very fine weather and convection cloud cannot be developed well in this region. So that's why the rainfall prediction along the latitude, we have a large amount of the rainfall along the equator. This is the tropical convergence zone. And in your region, subtropical region, according to the high pressure there, subsidence. That's why it's due to the subtropical high, rainfall is less than the other region. So this is the climate system. But the climate system is changed. That is a question of the IPCC. Is the climate changing? So the panel on the climate working during the fourth assessment report. In 2007, this fourth report, part 7. PCC consists of the three. I worked as the working group 1, physical science based. And in the fourth report in 2007, working group 1, they concluded at first, warming of the climate system is unequivocal. This unequivocal, this one is a little bit difficult to Japanese. It's very difficult to translate, for us to translate this unequivocal to Japanese. But this is the working group 1 message. Warming of the climate system is really apparent. Average temperature, sea, and the shrinking of the sun. And next question, change the climate. And it's called the model simulation, so-called general calculation model. I mentioned general calculation. So large-scale, global-scale calculation, by using the ocean and atmosphere coupled the circulation modeling. In this simulation, 90 global simulation center joined, and we concluded this warming is very likely due to the observed increase in atmospheric anthropogenic greenhouse gas concentration. So anthropogenic greenhouse gas concentration increase, that means that by human beings, very likely mean more than 90% of the model support this result. So this is our conclusion of the assessment report force in 2007. And the IPCC was celebrated by the Nobel Peace Prize. Yeah, as Professor Muduk introduced as one of the contributors to this IPCC, I was also celebrated by the IPCC. And the next assessment report, which was published in 2013, was used of the climate system book by the ocean heat content, and also Arctic summer sea ice extent. So in this case, very similar simulation were done, and the conclusion is the same, but the expression is different. It is extremely likely, not very likely. Extremely likely is defined as more than 95% of the model support this result. So this is our scientific output in 2013. And the August last year, assessment report 6 was published by the working group 1. In this report, is the climate changing? The climate. What climate? The very clear, unequivocal, that has warmed the earth and land. This is the conclusion, and the rapid change in the ocean, cryosphere and biosphere occur. That's the change. And the reason was also clarified. Observed warming is driven from human activity, with greenhouse gas warming. This is, you know this one, so this red part is the greenhouse gas contribution, but partly masked by also human effect. That is, we also could our activity with emit not only the greenhouse gases but the soot, the small particle. So that is work as a kind of the mask. So the cooling part also clearly quantified that contribution, and then this positive and negative effect, and then this global warming, the occur. That is the conclusion of the IPCC assessment report 6. So climate system is changing. So in that case, as the agricultural and the ecological drought increase. At this moment, we start to this question. There are a lot of uncertainty compared to the flood, extreme the event, the flood. The flood is clearly claimed by the model, also the theoretical terms, but this drought increase or not increase, this is a very long-term question. What is agriculture and ecological drought? You know, the natural climate due to the natural climate variability, precipitation deficiency, and temperature, high temperature. This is the meteorological drought. And then the water deficiency and the reduced stream flow, the inflow to the river, and the groundwater deficiency. This is a hydrological drought. And then the plant water stress and the reduced biomass and yield. This is the agriculture and ecological drought. So then our economy and the society, environment get a very big damage. So this the agricultural ecological drought increased or not. So the IPCC assessment report 6 in last August clearly said, so this is observed changes in agriculture and ecological drought, and a confidence in human contribution to observed changes in the world region. And your region, Mediterranean area, this is increased, and two dot mean the confidence in the human contribution is medium. Okay, so there are no high region. So the West North America and the your region is 2 dot. So very clear the high confidence on this change. And this is the observed change and prediction. Compared to the 1850 to 1900, according to the increase of the global temperature, what kind of the changes can be projected? This is the report from this is the result of the assessment report 6. But very chart we got assessment report 4th and 5th. So this dark green area increase of the annual rainfall, and this brown color area the decrease. So the your region here, the 10% decrease by 1.5 degree increase, and around 20% decrease of the rainfall according to the 2 degree global warming, and due to the 4 degree increase of the very large decrease of the rainfall. And the responding to this rainfall change, annual mean total column soil moisture change by using standard deviation. Absolute value, the drier region is very small of the changes there of the absolute value. So that's why we usually use the standard deviation. So -1 is the correspond to the once 6-year the drought case. So you can identify the projected result in your region. So this Mediterranean area is affecting the climate change increase with and more evaporation. So then the total column soil moisture the changes become more severe. So that is the hydrological situation. Why the region received this kind of the impact due to the climate change? One of the theoretical background was developed in 1960s. So sun energy is heated at the surface, and according to the temperature increase, the infrared radiation, upward infrared radiation is emitted. Infrared radiation absorbed by greenhouse gases, and then the temperature of the atmosphere is rising. So that is a green, you know very well. But not only these processes, but the following process is very important. At increase, that means downward long-wave radiation also increases. Can you understand that? This is the orange become red. Some more, that means. And also the wet area mass is generated more frequently. So then the day light, so going up. So in this way, according to the greenhouse gas effect, convection also accelerated. And in a narrower area, the warm air mass and that's why the heavy rainfall happens in a narrower area, and wider area is the subsidence. So then it's become drier. You know, I mentioned that physics was developed in 1960s. You know who developed this theory? Maybe you know all. Doctor. The equivalent, sorry, what happened? Yeah. Okay. And then he introduced the theory to the computer, and then I'm very happy to know the professor Manabe got the Nobel Prize in physics last year. I'm a civil engineer, not the geophysics scientist, but the reason why I'm working with climate system and water cycle is his supervision. I met him in 1993, and then after that, since my first meeting, he supported me, and I'm very happy to know Dr. Shukuro's the Nobel Prize. And so Okay. So the very important paper was published in 2015 by the Bill Rao and Dr. Kim of the NASA Goddard Space Flight Center, proceeding of the National Academy of Science Finance. They introduced this one. By using the 33 climate model, they analyze the mechanism of the dryness in your region. This dotted yellow line comes from the average 33 climate model for the rainfall. Rainfall increases nearby equator, and other place and a higher latitude increase. This is the vertical motion. The orange is upward, blue one is the substance downward. So as I mentioned, this is the hardware circulation. This is the equator, and then this is substance. So this is the hardware circulation. Northern hemisphere, hardware circulation in the southern hemisphere. Your country located here. And they analyze in more detail. How much change? This is the mean vertical wind. This changes. Very surprisingly, this hardware circulation core is narrowing. And the upward wind decreases here. But this downward wind there widely. This is the changes. This is upward, but this can downward. Downward become lower, but this is downward wind. So downward wind, substance area become larger. So this is the mechanism. So that's why the heavy rainfall occurs around the equator, and this wide region, lower atmosphere, the near surface become drier. So this is the mechanism. So this happens in our planet works. So that's why as the climate system changes, the agricultural ecological drought increases. So in that case, as one of the climate change adaptation, how can we adapt these changes? As one of the climate change adaptation measures, can we monitor and predict agricultural drought? Yeah, if we can monitor the agricultural drought or predict agricultural drought, we can take some countermeasure. So this is one of my science. Of course, by this prediction, we can also take various adaptation measures. Be able to introduce the possibility. So, what is the climate change adaptation measure? How can we develop the measures? Basically, climate model and observed data. And then we can downscaling, correct the bias, and uncertainty can be quantified, and the output can be used as an input into the hydrological model, and drought and flood, and the rainfall pattern can be humidity. These outputs should be connected with environment, socioeconomics, and culture and history. And then we can implement holistic impact assessment of the climate change. Based on this assessment, we can consider adaptation options, early warning, some quantity control by reservoir operation can be modified by using the sensor technology, and some modification of the land use and comprehension plan. Various adaptation options could be considered based on this holistic impact assessment. And then decisions should be made and implemented. The result of the implementation should be monitored and evaluated for reflecting the next decision-making process. And decision-making should consider this scientific uncertainty. We still have a large uncertainty at the regional scale or local scale. So that's why the scientific and engineering and socio-economic approach should be merged, and this kind of end-to-end approach on the climate change adaptation should be established in the country. So, for example, the quantity control. So, by using the reservoir and the prediction, we can squeeze the water if we predict the less rainfall or drought, or we can save the water for irrigation based on that the prediction. Prediction includes uncertainty, so that's why how can develop the such kind of methodology. That is one of the very hot topic of this hydrology. I have already developed such kind of a system, but today I will introduce some component. Before that, how can we assess this climate change? In the Mediterranean area, there is one of the JICA project. JICA requested me to assess the climate change impact in Tunisia. There is one big river, Niger, in Tunisia. So by using climate model and select a climate model which can express the regional climate in this region, and then we check the future change. Current rainfall, annual rainfall, and future rainfall come from the climate model after the bias correction and downscaling. And all of the selected models show the decrease of the future, the decrease of the rainfall around 2050. And this is the point estimation, but this is the major river, the Algeria. The downstream minus 20% April to September, and upper close to the Sahara Desert, percentage decrease. Much surprised. The theoretical hardware circulation effect appeared in this way. So then I recommended in my report of JICA project, it is virtually certain the drought will become more severe. So that's why, as place measure, here is the city Salem Dam here. Here. I strongly recommend to modify this dam operation, considering these changes in the annual rainfall. And the adaptation measure, we would focus on the monitor and prediction for urban volume. So as a background, we have been working to develop a soil moisture monitoring system by satellite. My algorithm is used as a standard the algorithm for global Earth, global land surface soil moisture product generation by NASA and also the JAXA. And this data set is very useful for the Earth land surface soil moisture monitoring. But we need more information. This data only land surface, but we need a root zone soil moisture for crop crop growth. So that's why we developed the dynamic vegetation model. The vegetation growth can be modeled. And the vegetation itself, this is the water. This is the lying water, and this is the standing water. By using the characteristics of the electromagnetic wave, we can monitor these vertical water and lying water separately. So Japan's sensor they can monitor, can observe these differences. And by using this, merge the remote sensing and hydrological modeling, that is the so-called data assimilation, we can see the root zone monitor, the root zone soil moisture. So only by using a satellite, this root zone soil moisture cannot be observed. But this kind of the coupled data assimilation, we have already developed the system. And so this is very useful. The rainfall prediction is include uncertainty. But if we estimate the root zone soil moisture correctly, this is the initial condition of the agriculture. So that's why if we have enough soil moisture in the root zone, we can grow the crop. And even the rainfall prediction is uncertain. So such kind of the system is very useful, and we applied this system to the prediction of the 2-year serious drought in Somalia. So the normal prediction have a very large uncertainty, but this green line is actual curve, and our prediction is a blue line. So we can predict the 2-year the lead time of the agricultural drought in Somalia. So we developed the system by combining Earth observation with the hydrometeor data and the satellite data and seasonal forecast and the global output. And then by using this real-time data management system, we can calculate the current condition of the soil moisture and also the crops. So, and then this coupled data can be run. We applied this system to North Africa, Tunisia, Algeria, Morocco. So the system can monitor the leaf area index and monitoring and the seasonal prediction, which includes uncertainty. That's why we get the ensemble rainfall prediction, and then this is input into the translation system, and ensemble drought prediction could be developed. So we compare this output with the national wheat production. Morocco, Algeria, Tunisia. this is the case of the 2000. In this year, the Morocco they experienced a very serious drought, and then the wheat production is very low. So the anomaly derived from this system in Morocco. But the Algeria, Tunisia, almost no one. So this is the result of the contribution to the agricultural drought. Is we done this system for prediction. This is a 3-month system. The wheat production, the harvest is end of March. So that's why we started the prediction January, and then this is actual result from the satellite, and this dark climate average. So this is a 3 months prediction on the January 1st. Algeria, Tunisia, almost average, but is a very low production of the food. So this is the ability of the 3 months prediction of the agriculture. I was invited to the COP22 Morocco, and they introduced this result. World Bank they request me to apply this system to northeast and northeast Brazil with year serious drought, and this is Kerala state, and very serious 5 years. So then we applied this system. This is the targeted area, 25 projections. So this is the monitoring, and this is projection 3 months. Root zone soil moisture now. And this is the area average prediction, and for example this grid, this is the blue one is the area average, and the pink green, and the various value can be the Ministry of Agriculture, and so this is the currently operating system. Country. So the Mr. Fukura-san, the Japan's embassy, requested me to give a talk 3 months ago. But I have never been in your country yet. So that's why it's very imagine your country. So then we applied our satellite to your country. Due to the very limited resources, the middle 10 days of August, the simulate, observe. This is the root zone soil moisture. From the satellite data is available since 2004. This sensor was developed by our Japan. Itself provided from the project, and following government developed our satellite, and this sensor advanced for the drone, and then we can continue to monitor the soil moisture. This is the soil moisture middle 10 days in August. So in 2013 have a wet year, but 2017 very dry year. So this is the leaf area correspond crop in August. Days average, that might be some impact of the snapshot of the rainfall also and also the focus on some region of the Jordan River, and I checked the agriculture production. That is most of the this is more than 200% the product. So this is very important export country. So and then the sowing season in September, October, Friday we focus on August, and from fall to 2018. We calculate some statistics as the anomaly index, the some value of each year by Asian standard deviation. So then this vegetation water content come from satellite, the express. This is come from the this monitoring system. Come from statistics of your country, the tomato production. Is normalized this anomaly index. The almost different this 2014, but the 2013 you have 17 you have less rainfall, and this the agriculture effect or low effect can be monitored through the methodology. So my system changes. Does agriculture ecological drought increase? Yes. As one of the climate change adaptation measures, can we monitor and predict agricultural drought? Yes. But I have not get some result in North Africa, Brazil. It can. This is my talk. Thank you very much for your attention.
Thank you very much, Dr. Koike. It's really very impressive and very high level of scientific lecture. It's really, we are really looking forward to have such kind of experience in Jordan. We are really looking for that. The most important thing that I really notice in your culture, I hear that we are in the critical situation, our region, especially Jordan. And this will be a very good sign for us to work more hardly in the climate change. Thank you very much, and let me ask His Excellency Dr. Hazem al-Nasser for his remarks after this lecture. Dr. Hazem al-Nasser was ex-minister of water irrigation in Jordan, and he has a very good work research in climate change and water scarcity in Jordan. And I think he is the most well-known figure in the water issue in Jordan, also one of the good scientists in this field. You're the floor for you, your experts. Can you give me the host, Dr. Koike?
Okay. Are you okay?
Yes, thank you.
صباح الخير وكل عام وأنتم بخير. Your Excellency, Ambassador of Japan and the Hashemite Kingdom of Jordan, Your Excellency Dr. Ahmed Al-Ajloni, President of the Al-Balqa Applied University, our distinguished guest, Professor Koyaki from Japan, ladies and gentlemen, good morning. After we heard the scientific and the academic background of the impact of climate change on water and agriculture by our distinguished Professor Koyaki, I would like to highlight few issues related to water and climate change, in particular related to the Hashemite Kingdom of Jordan. When it comes to climate change in our area, water at the heart of climate change. And when we talk about climate change and the variability we heard from our distinguished lecturer, for us as Jordanians, maybe the Middle East as a whole, climate change means more water shortage, which adds to the challenges that we have already in this area. So just to give you a brief description, I will not be long, but I will try to bridge the scientific, economic, and political aspects of climate change and water. Jordan, as mentioned by the president of the university, among the most scarce countries in the world. Per capita availability is less than 100 cubic meter per year for all uses, which is very low by all means and standards. This mainly due to prevailing climate conditions, population growth. Jordan hosted waves of refugees and displaced persons as a result of regional conflict. The impact of influx of refugees on Jordan's water resources as an immediate impact is much higher than the impact of the climate change, because increasing demand in emergency and crisis management time is much and more damaging to the precious water resources that we have. So when it comes to climate change, the climate change actually pressured the already stressed water resources, which is very little. We don't have major rivers, we don't have major lakes. We have some groundwater and some transboundary water resources, and the groundwater being overpumped. So these challenges impacted so many issues related to water. First of all, people are not getting water. This is the bottom line. Jordanians last 2-3 years getting water once every 2 weeks, which is low by all means. Water became expensive because development of scarce water resources is a very expensive business. And over the last 50 years, Jordan developed all accessible, easy accessible water resources. And now we have to look for remote ones which are beyond our financial capabilities and beyond affordability of people to pay for such a very expensive water. A Jordanian pays an average like $2 per cubic meter of water, which is very high among all standards and tariffs in the region, where cost is about $4. Cost is $4 per cubic meter, and Jordanians pay $2. $2 is very, very expensive for the people. If we consider the income of people and how much they pay for water and sanitation, this represents maybe 5 to 7% of their income, which is high by all standards. Most of the people pay between 0.5 to 1, worldwide, between 0.5 to 1% of their income. So those are some of the challenges. When it comes to climate change, we did some very important studies, and I was a contributor to this research personally between 2013 and 2016 with Stanford University. And simply we found that rainfall amounts, especially in the southern east and southern west part of Jordan, will decrease by the end of century between 15 to 25%. This is huge. This is very scary because already the groundwater recharge rates at the edge. If we lose that amount of rainfall, this means we will not have groundwater recharge, which is a main water supply for Jordania, especially for drinking water. So this is about the financing. Of course, one of the additional challenges besides financing and cost and remoteness of the supply and the population growth and the increasing demand is how to channel the new technologies to help alleviate water shortages in Jordan. In particular, moving from water to digital water business. And this needs a lot of financing, and this needs new infrastructure. Also, it needs a new culture and a new capacity building, which we are really lacking. Maybe your university can help with that, because this is a very important aspect to all of us. When it comes to agriculture, as mentioned by our professor, the climate change impact on rain-fed agriculture in Jordan will be huge, because models and simulation predictions said that, again, by the end of the century, rain-fed agriculture will lose about 18% of its rainfall amount or water supply, which means we have to come up with additional water supply to mitigate these losses. I don't think we will be able to do, but the end result will be impact of the sustainability of fed agriculture, rain-fed agriculture in Jordan, especially along the mountain area. So those are the challenges in brief, and there are many additional technical ones related to efficiency of water use, integrated water resources management, etc. But how Jordan responded to these challenges over the years? Jordan worked in so many fronts, because definitely there is no magic solution to solve this chronic water problem. Otherwise, we have done it many years. And I think Jordan will continue to live with this challenge for many generations to come. So the Jordanian government over the years worked over so many fronts, as I said, to alleviate the water shortage, starting with demand management, educating people, introducing water conservation measures and technologies, especially in the Jordan and the agricultural sector, irrigated agriculture. And always I give example just to demonstrate how Jordanian farmers are really efficient in water use. I said the amount of water that we used to use since 2006 or 5 did not increase when it comes to agriculture. On the contrary, decreased by about 20%. And today, our agricultural produce increased 2 to 3 times with the less amount of water that we used to use 20 years ago. This is evidence about how Jordanian farmers work in efficiency over the years, especially in the Jordan Valley. So this is part of the responses, is the demand management, water conservation, and increasing water supply. Increasing water supply, with the exception of the DC project, we could not increase major water supply quantities over the years for the reasons I said. It's so expensive. If we want even desalination, is not an option for Jordan because the closest sea is about 400 kilometers away from the demand center. And to convey and desalinate and distribute, we need billions of dollars. And with the influx of refugees and their impact on the economy, Jordan is really not being able to do this from the physical budget. And we tried with the international community over the years, but until now, actually there is no success in doing that. We focused as a response to the water challenge on circular economy, in particular wastewater reuse. And Jordan is one of the Middle Eastern countries where we reuse 100% of our wastewater. And this is a big achievement for a country with modest infrastructure and modest financial return. And we worked a lot on integrated water resources management, how we integrate all the resources under one water cycle. But unfortunately, due to external elements, mainly conflicts in the region, as well as influx of refugees, and now the challenge of climate change, long-term planning for the water sector is not possible. Because when we start to do proper planning, we surprised by an influx of refugees, like the one happened in 2012, 2013, where 1.5 million Syrian refugees came to Jordan almost overnight. And those represent about 20 to 25% of the total population. So nobody in the world can tell Jordanians about long-term planning when it comes to the water sector unless we have access to the funds of the world, which is not the case. That's why long-term planning, people a lot, every day they say, water planning, where is this? This could not happen because of the external elements. Iraqi war, Syrian civil war, influx of refugees, climate change. Those external elements beyond our economical, social capabilities, as well as technical, infrastructural one. One of the solutions that we worked a lot on it, and our friends in Japan also very much pro such a measure, which is utilization of renewable energy in the water sector, in particular solar energy. And I can tell you the only water sector in the Middle East with 20% of the energy mix is from solar energy is the Jordan's water sector, which is a big achievement in terms of mitigation for climate change, although we did not contribute to any of the impacts of the climate change. Jordan is not an industrial country, but we receive the impact, the negative impact of climate change. So renewable energy maybe is one of the hope and light at the end of the tunnel for maybe a cheaper water production over the coming 5 years. So I try to be short, brief, straightforward, and this is the message that I would like to tell you about Jordan's water sector. And if you allow me, can I ask Dr. Koyake just one question? If he's hearing me, yeah, please. I want to ask him, because we listened to a very fantastic lecture, very scientific. But I want to ask him to tell us in one statement, quantitative statement about the impact of climate change on Jordan. Is this negative, positive, and how much? This is the statement I think we, the audience, we would like to hear from Professor Kawayaki if this is possible. I thank you very much, and I thank the Al-Balqa University and Your Excellency President Hajroni for inviting me to contribute to this important seminar. I also want to take and seize the opportunity to thank our Japanese friends and Japanese people for supporting Jordan over the years, in particular the water sector. And Japanese financial and technical support to the water sector really made a change over the years. And for that, Your Excellency, we thank you very, very much.
Thank you, Your Excellency, Dr. Hassan Nasser. Professor Toshio, you have a question?
Okay, thank you very much. The purpose, as I mentioned, not only one discipline, but the cooperative, the disciplinary cooperation, interdisciplinary cooperation, and also that value should be shared with the society. So transdisciplinary, the cooperative framework should be developed. That's why I cannot say that this is a quantitative solution of the climate change. But as you mentioned, from the point of the energy, or from the point of the water saving for agriculture, we need to evaluate each adaptation methodology based on the assessment. Then we can try to find the solution. That is my idea. So my response to the question is that we need to work together, the interdisciplinary and transdisciplinary, to get that question and to get the answer to the question.
Thank you. Thank you. Thank you, KOIKE, and thank you, Your Excellency, for your very question. Now we are coming to our closing time for our workshop. And kindly are requesting His Excellency, Dr. President Dr. Ahmed Al-Doli, to give his closing remark with text.
Well, you know, I'm not an expert in this field to give the closing remark, so I will try. Okay. First of all, thank you, Professor KOIKE, for your fruitful lecture. Thanks a lot. And thank you, Dr. Hazm Nasser, for your comments. And thank you, Mr. Ambassador, for choosing this topic. It's really very important topic in Jordan, because wherever you go in Jordan, always we talk about water. You go, everybody in his house, they talk about water. Is there is water today or not? Is that right? That's what we do in all our life. So thank you a lot. And I think we need to gather and we need to get Japanese experts to do like a prediction center, probably scientists in Al-Balqa Applied University and Japan, or JICA probably. We need to bring experts to do some kind of center for prediction in global warming. And I guess even war probably contribute to global warming. So I think we need to do more of scientific research and what's the effect of global warming in Jordan even. So in the end, I thank all the audience here. And I thank you, Mr. Ambassador. I thank Dr. Hazm Nasser. I thank everybody. And I hope we will see you again soon in next lecture. So thanks a lot, everybody. And see you very soon, hopefully. Thank you.
Thank you, Excellency, for this remark. And we will have now and two questions from the audience from the board and here, and one question from people who are online. So please ask your question.
Thank you for this important workshop about climate change. My question is for Professor Toshio. He spoke in his presentation about the uncertainty in predicting climate change. You might know, and you all know, about the Kyoto Protocol. Now there is two contributors for the climate change. One of them. I hope Professor Toshio is still with us.
Yeah, I'm here. Sorry. You are going to ask two questions?
Yeah, I just have one key question about the uncertainty in predicting the climate change. There is two reasons I believe that contribute to climate change. One is human activities related, and the other one is beyond our control, which is the obliquity of the Earth axis tilting. For example, in the last 41,000 years, that tilting angle changed between 22 degrees to 24.5 degrees. In terms of human activities, the humanity has added the problem, and we were aware of it since Kyoto Protocols in 1997, and we ended up with London Declaration in 2021. But I believe most of the research are focusing on human activities, and very little research addressed maybe the major contributor, which is the Earth obliquity in predicting the climate change and drought regions. So what do you think of that? And my second question, shall we in Jordan, from your viewpoint, accelerate the adaptation of new technological development in the water sector in order to help ourselves in solving the problem? Not limited to desalination, as His Excellency mentioned, but maybe in water reuse. What do you recommend on that? And thank you very much.
Okay, thank you very much. They are very important two questions there. With regard to the first one, your country, Jordan, and as a dry country, you have a lot of the experiences. I heard in your language there are 15 or 16 level of the dryness. I'm not sure that such kind of the culture and also the life experiences you have. So based on that, your culture and social mechanism, how can you adapt to the unexperienced change? So as IPCC identified, this change is unequivocal, and this the caused by human being by the increase of the greenhouse gas the emission. So for example, the Dr. Naber analyzed the paleoclimate situation compared with the current change of the climate. The very clear the change can be identified. So I think based on the cultural social mechanism we accumulated in past, we need to adapt. So for that purpose, this is closely related to the second question. We need to understand the mechanism and also the uncertainty itself, and try to quantify, but the quantification is limited. So that's why based on our understanding, mechanisms, quantification, and uncertainty, we need to make a decision. For that purpose, based on assessment, we need to develop a list of the adaptation options and economic and or social evaluation, and then we need to take the option based on the experiences. There is no unique, no universal answer, but it depends on each country, culture, and experience and social condition. That is my the consideration. This is the combined the answer to your first question and second question. Is it okay?
Thank you, Dr. Koike.
Okay.
We have a question from the audience in virtual. I can see Dr. Hiba Karabshi.
Hello,
Yes, go ahead.
can you hear me well?
Yes.
Yes.
Yeah. Good afternoon, everyone. I'm Dr. Hiba Karabshi from the Faculty of Agricultural Technology. I have a question to Professor Toshio regarding the kind of adaptation for climate change that is very suitable for Jordan. For example, we have two kinds of adaptation. The one which is the pro-adaptation techniques, for example, in selecting what is the best or the good choice of crops that will use little amount of water, which are the drought-tolerant crops, or the other kind of climate change adaptation, which is following the crisis, which is like using some certain kind of techniques like water harvesting. So what is the best for Jordan, to choose the pro-adaptation techniques or the one that following the phenomena? Because we are in the Faculty of Agricultural Technology in the Water and Environment Resource Management Department are interested in this science, and we are trying to develop a laboratory which take care of this kind of research. So this is the end of my question.
Thank you.
Okay, thank you very much for your very, very thoughtful idea. And of course, the selection of the crop to adapt the change in the water harvesting, and also His Excellency mentioned that some renewable energy mixing. They are very effective, I think. I think our target is maybe societal stability, and also the quality, keeping the quality of life. To support these social objective, one of the aspects is the water, food, energy nexus, the conservation. So the water, food, energy, these are closely related together. So how can we develop this kind of comprehensive methodology, not only by the agricultural scientists, but also in cooperation with hydrology scientists and also the energy engineering. So such kind of coordinated framework may be necessary to find a reasonable solution. So university has such kind of the function to develop, as I mentioned, the interdisciplinary framework to solve the problem comprehensively from the various point of view, and communication or dialogue with society is a very key. I think the role of the university to develop the adaptation methodology or society which can adapt to this change is very, very important in observe the university role. That is my response to you. Is it okay?
Thank you very much, Dr. Koike. And will be the last question because His Excellency has another commitment. He has to be on time. And let me, in your behalf, thank you very much, Dr. Koike, on behalf of Al-Balqa University and the audience. And let me express our very grateful and thank you very much for very high-level scientific lecture. Thank you for our audience. Thank you, Your Excellency, Mr. Shimazaki, Your Excellency, Dr. Hazem Nasir, Your Excellency, Dr. Ahmed, President of Al-Balqa University, to host such a very high-level academic workshop. Thank you very much, and let us give a very big clap to our audience.